Okay, so today we're doing experiment number 4, and the purpose of experiment number 4 is to ultimately determine the concentration of iron in a vitamin. However, the way that you're going to go about determining the concentration of iron in a vitamin can also be used to determine the concentration of any unknown solution. So it's quite useful in that sense. You will be determining the unknown concentration of iron in a vitamin using a colorimeter. And with this pre-lab question, what you're going to see is that it is basically going to be the same process of determining what your unknown concentration is. However, for this particular question, it's looking at red fruit punch as opposed to iron in a vitamin, but the process is still pretty much the same. So, for this question, we have a jar of red fruit punch, and we're asked to determine the concentration of red dye in the fruit punch. Very similar to what you'll be doing with the vitamin. You will be asked to determine the concentration of iron in the vitamin. So same sort of process here. Now, it is known that a 0.0010 molar standard solution of red dye absorbs with an absorbance value of 0.77. So we have something to compare it to, which, when you go to determine the concentration of iron in a vitamin, you will have something to compare it to as well. Now, you decide that you are going to test your fruit punch in your colorimeter, but the colorimeter has a bit of a drawback in that there is a specific range of absorbance values that you need to have your absorbance values in between in order for your data to be considered reliable. And with colorimeters, this is between 0.1 and 0.9. So all of your absorbance values, the experimental values that you take using your colorimeter, need to be in between this value. And if they're not, then they're not reliable. Now, in most instances, your values are going to exceed this range. So, as a result, you have to do some dilutions, meaning you have to make it less concentrated in order for your absorbance values to fall within this range. Okay, so if it exceeds 0.9, you have to do some dilutions. On the other hand, if your solution is too dilute and it is below 0.1, then you have to concentrate it in order to get an absorbance reading higher than 0.1. In most instances, what you'll see is that your solution is going to be too concentrated. And that's exactly what's going to happen when you do experiment number 4 with the vitamin. You're going to make a vitamin solution, and it's going to be too concentrated, meaning you're going to test it in the colorimeter, and you're going to have an absorbance value higher than 0.9. So, as a result, you know that you can't use that number as a reliable data point. So, you have to do some dilutions. Okay? In order to do some dilutions, what you do is you take your concentrated solution, and in this particular example, you take 5 mils, okay, and you take 5 mils of that concentrated solution, and you add 95 mils of distilled water so that you have a total volume of 100 milliliters. This is dilution number 1. So you're on your way to diluting your solution, the one that's too concentrated, the one that's giving you an absorbance reading higher than 0.9. Okay, same thing goes with the iron in the vitamin solution. So you have dilution number 1. Now, you look at this, and chances are it might give you an absorbance value that is also higher than 0.9. So you can do an additional dilution where you take 5 mils of dilution number 1 and dilute it to 100 mils using distilled water. This is dilution number 2. Okay, when you take this dilution and stick it in your colorimeter, you actually find that it gives you an absorbance value in the range that you desire. So what you can do is using this information, using the absorbance value that you have for dilution 2, and using the amount that you diluted with, you can back calculate from the least concentrated and determine the actual concentration in that concentrated solution that was too concentrated for your colorimeter to accurately read. So you are going from least concentrated to most concentrated. Okay, and that's exactly what you're going to do when you test with the iron in the vitamin. You'll have this concentrated solution, you'll dilute it, you'll check that, see if it's between the absorbance value range that we want. If it's not, you'll dilute it again. If that you check that, if it's between the range, then you can back calculate, just as what you're going to see here, to determine the concentration of iron in your original solution, the one that was too concentrated for your colorimeter to read. Okay? Now with this experiment, I do want to point out to you that it's very important that you pay attention to the volume that you are using to dilute with, and that you're very careful when diluting. This is a quantitative experiment, meaning you have to pay attention to whether or not you take 5 mils out or 10 mils out or anything like that. So make sure that you're paying attention to what you're taking out, how much you're diluting with, and that you're doing everything carefully. Okay, so how do we figure out, in this example, how do we figure out the concentration of red dye in the original solution? Okay, that's ultimately what the question is asking for, and that's ultimately what the experiment will be asking you too. What is the concentration of iron in the original iron solution? Okay, so we have to work backwards. So if you have read the introductory sections, you'll see that when you have an absorbance value and a known concentration, you can actually use that to your advantage. So what we're doing is we're going to find the concentration of dilution number 2. So dilution number 2 we saw has an absorbance of 0.21. Okay, and notice how I'm not writing any units here. Absorbance does not have any units. Okay, so 0.21, and if you read these introductory pages, what you can see is that you can compare it to a standard solution. So if we remember from the first paragraph of this problem, we know that a standard solution of 0.00010 molar standard solution has an absorbance of 0.77. So we can use this as a conversion factor to determine the concentration of red dye in dilution number 2. So this is our conversion factor, and obviously we want to be left with molar. So if we set this up and we multiply by 0.00010 molar, divide by 0.77, you see that the absorbances, they essentially cancel themselves out, even though they don't have a unit, and you're left with big M. So this will give us the concentration of red dye in dilution number 2. This is exactly what you will have to do with your iron. You will have to find an absorbance of your iron and compare it to a standard. So when we do this calculation, we get 2.7273 times 10 to the negative 5 molar. Now, obviously we have to account for significant figures here. And if we look in all of the numbers that we have, everything has 2 significant figures. So for this problem, my final answer would have to also have 2 significant figures. So for this problem, my answer would be 2.7 times 10 to the negative 5 molar. So we've now determined the concentration of red dye in dilution number 2. But if you recall, we want to know the concentration of red dye in the original concentrated solution. So we have to back calculate. Okay, so now that we've compared it to a standard, we have a concentration. Okay, now we need to work backwards. So now we need to determine the dilution, or the concentration of red dye in the dilution number 1 solution. Okay, we already have it in number 2, but we need to figure it out now in dilution number 1. So if we're looking for the concentration in dilution number 1, okay, well, we know that with this, since we're doing dilutions, we know that we have to use M1V1 equals M2V2. Okay? Because that's what serial dilutions use. We couldn't use it in this first problem here because we had to initially get a concentration, but now that we have it, we can now go on to use M1V1 equals M2V2. So if I'm looking for the concentration in dilution number 1, I have to know the volume and M2 and V2. So basically I have to know the volume that I took out of dilution number 1. And I know that I took out 5 milliliters. Now, in terms of M2 and V2, I know that my concentration of my dilution number 2 was 2.7 times 10 to the minus 5. But remember, we have to use the whole entire number. We don't want to use the rounded number because that will give us an incorrect answer. So make sure that when you're doing these, you use the whole entire number. So my concentration of red dye in dilution number 2 is 2.7273 times 10 to the minus 5. And we diluted that to a final volume of 100 milliliters. So I have everything except M1. If I solve for M1, meaning the concentration in dilution number 1, I get an answer of 5.45455 times 10 to the minus 4 molar. Now, this is the concentration of red dye in dilution number 1. But again, if this was my final answer, I would have to account for significant figures. And again, only 2 sig figs. Okay, this has 2 sig figs. This, even though we have to use all of the numbers, we know only 2 of them are significant. This one has 4 sig figs, but since we're multiplying and dividing, we know we have to go by the smallest number. So our final answer should have 2 significant figures in it. So what I've done is I have calculated the concentration of red dye in dilution number 2. And using M1V1 equals M2V2, I've calculated the concentration of red dye in dilution number 1. And I'm going to take it to the last step and figure out the concentration of red dye in the original solution that was too concentrated for the colorimeter to read properly. And this is exactly what you will do when you test your iron. So, the last part of your pre-lab question, and again, very similar to the calculations that you will do in your actual experiment, you will have to now calculate the concentration of red dye in the original sample of the fruit punch. Okay, so we have here, we want the concentration of the original solution. So again, we will be using M1V1 equals M2V2. Now M1, that's the concentration in my original solution. So you can name it M1, you can name it X, it doesn't matter, okay? And we know that we took 5 mils of that original solution, okay, and we diluted it, okay? And we figured out that the concentration of dilution number 1, and remember, we have to use the whole entire number. .45455 times 10 to the minus 4 molar, and that was 100 milliliters. So what this is saying is we took 5 mils of our original solution, we diluted it to 100 mils, but we know that concentration. So if we solve for M1, we get a value of 1.0909091 times 10 to the minus 2 molar. So again, accounting for significant figures, we know we can only have 2 significant figures, okay, because we have 2 here. We know even though this is a big long number here, only 2 of them are significant. and here we have 4, so since we're multiplying and dividing, we know we have to have 2. So our final answer for this is 1.1 times 10 to the minus 2 molar. So 1.1 times 10 to the minus 2 molar of red dye in the original concentration. So what you see, what we've done here is we've gone from the least concentrated to the most concentrated. And this is what you're going to do when you test the iron in the vitamin solution. You're going to generate a very concentrated vitamin solution that your colorimeter won't be able to read properly. You're going to dilute it. You're going to most likely dilute it again. So you will end up doing step number 1, 2, and 3 in order to determine what the original concentration of iron in your vitamin is. Okay? If you have to do a third dilution or a fourth dilution, you simply do steps 2 and 3. They're the exact same steps. You simply do them again. Now, one area that I will point out to you is that when doing experiment number 4, this value here, this dilution amount, will change. Okay, you're not going to be taking 5 mils out of your original stock concentration. I believe it is 20 mils. So just make sure that you pay attention to that. But aside from that, M1V1 equals M2V2 is what you will use after you do part number 1.